Day, and this is our last week of classes, so we've made it through this crazy semester. Just a couple things. So next week already is your final exam. I'm going to open it up to give you more flexibility of when to take it, and so it's scheduled, I believe, for Wednesday, but I'm going to let you take it any time in the window, Wednesday or Thursday. Okay, so anytime on Wednesday and Thursday of next week that you want to take it, feel free. And I'm going to give you um, more time than what you need. So I'm thinking, I think it's scheduled to be like a 2 hour exam, but let's do a um, the length of movies these days, like The Irishman or something like that. I'll give you like 3 hours, which you will not need for the exam. Okay, so anytime, Wednesday, Thursday of next week, and you have 3 hours to take it. I'm thinking I haven't made it up yet. I mean, some of it is, but I haven't finalized it yet. But it'll be somewhere around, I don't know, 50, 55 or so questions, and it's going to cover all of the chapters, including chapter 8 that we're going to cover this week. And I guess you've already done a virtual lab related to energy. Okay, so we're going to talk about thermodynamics this week. Okay. So any questions? Study guide? Yeah, so I'm planning. So the only topic that you really haven't been tested on so far is really valence bond theory, and I'm going to go through a couple questions here in Chem 101 today, and then all of this new chapter. And so I'm going to post some questions as homework on Chem 101, and so you can do some questions on that as kind of practice. And then other than that, you're free to go back to the practice midterm homework assignments, and you can attempt those again. Those should be still open for you, and they're all multiple attempts. And so that's probably the best way to study, because the questions on the final will come from that same pool of questions. And so it'll be very similar to what your midterm exam questions were. Since it's not an ACS final, you kind of know what questions to expect. Okay. Any other questions about the final? Okay, so does it Chem 101 from last Monday? Yeah, yeah, the Chem 101s, I guess they expire a couple hours after lecture. So if you didn't get a chance to complete some, it's not going to affect your overall participation grade. I'm just going to be looking for, have you done around half over the whole semester, so you can, miss half of them, and it won't influence things. Um, oh, the audio problem, yeah. I The ones from there, I'll see if I can, yeah, because it was an audio problem, I'll see if I can reopen those as homework. Um, and I'll send an email if I'm able to do that. Yeah. Um, Evenly spread out. Yeah, so some other questions about the final is the exam will be spread out. So just because I haven't asked any questions on midterms about chapter 8, that doesn't mean that the final will be like heavily weighted. So you'll just get a few questions related to the new material from this week, chapter 8. So maybe, I don't know, like 5 total questions related to the new material, and then all the rest based on the previous stuff. And then the Alex homework, that's actually 50-50. So 50% or half of your Alex grade is going to be on the pie chart at the end of the semester. So I think I've got it until final week, I believe, like the Friday of finals week. So next Friday, I think, is kind of the cutoff. So you can, do open pie, complete all kinds of different topics after your finals yet. And then the other half is the average of all your weekly assignments minus your lowest two. Okay. Whoops, you can't see that. There you go. Okay. A curve on the final. If it were the ACS one, then it would be like a what kind of curve is usually like a 30% curve or some crazy thing like that. It's likely that there will be a curve on the final. I just have to see kind of what the grades are for it. But I haven't given my own final in years and years. So it's likely, yeah. So it'll be, I'll curve it to a C plus or whatever I was doing the midterms. I think those were like a B minus or something like that. So I'll curve it, to that same grade as what I've been doing for the midterms. Yeah.
Hey, Professor, what do you mean when you say the average weekly score for Alex? Like, what would that be?
Those are your, the ones that were due like every Tuesday? Um, those objectives. Yeah, so all of your weekly objectives.
All right.
Yeah.
So we just did all the work every week. We're good.
Yeah. So you should have pretty good in the pie chart, and then if your average scores every week was pretty good, if you have a couple of oopses in there, those are going to go away. It won't show in your grade book yet as being kicked off, but at the end of the semester, like next Friday, when all the grades kind of finalize in Alex, then you'll see your grade book. It'll reflect this, the lowest two taken off, and then your pie chart completion at that point. Yeah.
All right.
Yes. So the May 8th, is that, let's see, is that next? I have to go to the calendar. Yes. Yep. So 11:59, May 8th. You still have to work on your pie chart. Yeah. Okay. Any other questions I missed here? I don't think so. Yeah. No classes next week. It's all just for finals. Yeah. Okay. So again, there won't be any like practice final homework assignment on Blackboard because really you've got those already. And then the stuff from this week will I'll put it on Chem 101, some extra questions on there for you. Okay, so let's just kind of review that last lecture that I posted last week. So this was like the Thursday, Friday workshop lecture. So if you haven't watched that, make sure you watch it because there'll be a couple questions related to these that we're going to go through Chem 101 on the final. And one of them will be just like this, okay, where you're given, kind of a complex looking molecule. When you go on to take organic chemistry, this will be very, very familiar to you. But so it's the video. It's, what was the date of last week? I guess I've got it entitled April 23/24. And then it's related to valence bond theory. So it's April 23rd, 24. And then I've got it as valence bond theory. And then it also has midterm 3 solutions. Okay. So if you want to fast forward through that or whatever, feel free. So this is the new material that, yeah, there will be some in the final. Okay. All right. So for this question, let's see how many people have attempted this yet. Whoops. Okay, not too many. Okay, so only five. So this may be something, more people have to watch the video kind of thing. So the gist of that lecture on valence bond theory is being able to count sigma bonds. Okay, so when you see a sigma bond, that's just single. Okay, so in this molecule, all you're doing to count the sigma bonds is you're just counting, literally, you're just counting all the single bonds. And in multiple bonds, like in some of these, one of them will be sigma. Oh, there's a delay in my whiteboard thing here. Huh. Come on. There we go. Okay, so one of the bonds in a multiple bonding arrangement will be sigma, and then the other one will be pi. Okay. And then if you would have a triple bond, for instance, one is sigma, and then you've got two pi's. Okay, so you'll see that, pi orbitals was overlap between p orbitals kind of vertically, whereas sigma is overlap where they're kind of on that same uh, position between the atoms themselves. Okay, so sigma is kind of putting electron density between the atoms, whereas pi's are above and below, getting the overlap that way. Okay, and so if you're counting this molecule, then you're just kind of going through, and I don't know if we start here, so that would be one, two, yeah, let's do maybe all the periphery ones. So 1, 2, 3, 4, 5, 6, 7, 8, and then let's go in the rings. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So 23. I must have counted wrong because that's not an option. Let's see. 2, 3, 4, 5, 6, 7, 8, then 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23. I keep getting 23 here. And I can't mark it off here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 16, 17, 18, 19, 20. Yeah, I'm all over now. Yeah, I might have to redraw this and actually, let's see. Yeah, let's do this. Crap. Okay. So all we're doing is just counting the singles. There were 24? Okay, good. Okay. Okay. As long as some of you are getting 24, so you don't have to waste time here. Okay. So yeah, just counting the singles. Okay, good. I guess it's too early for me, even though it's past 11. But yeah, so 24 sigmas, and then this will be easier to count the doubles. And so you've got 1, 2, 3, 4, 5, 6, 7 pi's. Okay, so I guess the answer then would be A. So 24 sigma and 7 pi's. Okay, so it's literally that easy. Wherever you see a double line or a double bond, one of them is pi, the other is sigma. Okay, and then you just count up. Okay, so any questions about counting sigma pi's here? Okay, the other question So I've got it as VB valence bond 2 is now related to overlap. And so it's asking in this molecule, so the strategy would be to draw its Lewis structure. Okay, so this one, if you go through those steps to draw its Lewis structure, it would be that, which again, there's a delay here. Huh. Okay. And so it's asking this bond here. Okay, and here's the other gist, if you will, from the lecture last week, is you have three types of hybridization. So you've got SP, SP2, and SP3. Okay, so, minute lost. There we go. Okay. Let me see what Wi-Fi I'm on. Oh, that's why. Just a second here. Problem with the mirroring aspect here. Okay. It's not picking up my iPad this morning. Let me start again here. Okay. Right. Okay. This really sucks here. Hmm. It says it's on. There we go. There we go. Okay, cool. All right, so there's three types of hybrid orbitals or hybridization that you can have, when you're bonding. And just look at this superscript. Okay, so that tells you how many atoms are bonded to a particular central atom. Okay, and so for instance, and I guess it's not really just um, atoms per se, but it's, I guess, electron pair domains is maybe the best way to look at it. Okay, and so if you're looking at, let's say, hybridization of this carbon, okay, so how many separate electron pair domains do you have around this carbon? Okay, and so to look at that, you have really one here, okay, so a bonding pair, another one there, and then you count double bonds as just one um, pair domain, really. Okay, so you've got, if you want to say it, this is not totally not scientific, but the question here is really like how many things, okay? Okay, and by things, it could be like lone pairs or atoms around it. So how many things are around a particular atom? Okay, and so in this case, you've got three things around it, right? You've got that oxygen and two fluorines. And so the hybrid will be one less. So this superscript will be one less than that. So if you have carbon that's surrounded by three things, in this case, then the number will be 2 is this superscript, right? So it'll be sp2 hybridized, okay? And then this oxygen is also surrounded by three things, right? Because you've got two lone pairs and another atom there. Okay, so this would be then an example of sp2 for this oxygen and then sp2 for this carbon. Okay, so the answer here is sp2, sp2. Okay. Things like this, if you were to have like methane, now this is surrounded by four things, or four atoms in this case. Whoops. Okay, and so that means that it will be sp3. Okay, so one less. That superscript is always one less. Okay. All right, so that, those are the two things or two concepts. I'm using things a lot here. Two concepts that are good to know for the final exam. So I'll have some question about hybridization. I'll probably just give a molecule. It may not even be as complex as this. It'll just be like some molecule and ask what's the hybridization of the central atom. Okay. Does the S make sense, or is that easy to rule out? Yeah, the S is just there because you're overlapping s orbitals and p orbitals. Okay, so you're combining s and p's together, and so then you end up with a hybrid orbital that kind of looks like that. Okay, so that's if you have sp3 and sp2. Yeah, so you could have a situation, what would be an example? Where you have a combination of sp3 and sp2. So I guess, whoops, not s, where you've got carbon like this. Like that, we'll say. Okay. Okay, and now if you look at this carbon would be sp3 because it's surrounded by four substituents, right, or four atoms, okay? But this carbon would be yeah, so this carbon would be sp2, right, because it's only surrounded by 1, 2, 3 things, right? And then likewise, that would be also sp2 because it's surrounded by 1, 2, 3 things, okay? So that's an example of one, simple molecule where you've got kind of both going on, okay? Or, you could also have this one, right, where this is sp3. This would be sp, right, because it's only surrounded by two things, okay? And so that would be sp, that's also sp, okay? And the central atom, yeah, for these, I guess there's really no central atom per se. I guess that one would be the central, but if I would ask a question related to this, I would have to, draw it out for you, so that you know what the molecule looks like. Okay, it wouldn't just be kind of like this, right? I can't put it as just the chemical formula. Okay, so I have to actually draw this out and then ask, this, and then maybe put a little A here. This carbon, what is its hybridization? Kind of like that. Okay. So any questions about that then? So yeah, if you watch the video, I go into more detail about like what the heck do these mean, like these SPs, how they kind of overlap. I won't be asking, detailed questions really related to this per se. So really the questions are really on application. So, draw the Lewis structure, see, do you have double, single, triple bonds in there? And then, just use this. There's actually in the slide, there's a really nice table that summarizes it too. So SP means that you're surrounded by two things. SP2 is 3. SP3 is 4. Okay. All right. Okay, so that took up more time, but yeah, it's good, yeah, because that was a recorded lecture anyway. So okay. All right, so this chapter is something that we are going to revisit in 132. So if you're going to take 132, hopefully face to face next fall, we'll kind of get back to these concepts. And so we're just going to really today talk about some definitions. And the first one is it's really the first law of thermodynamics. It's actually known as, and another way to say it, it's a law of conservation of energy. And so this is saying that energy can't be created nor destroyed. It can only be converted from one form to the other. And the forms that we have are really just two, right? It's kinetic or potential. Okay, so you can convert between those all day long. Okay, and there's subtypes of these, like you've got electrical energy, for instance. Okay, that's a type of kinetic because things are moving around, like electrons are moving around, right? Potential energy is energy of position, and so that would be what we're going to talk about probably tomorrow. Bond energies, like how much energy is, if you have this molecule, how much energy does it take to break this bond? To break a CH bond, okay, and it'll be in something kilojoules per mole. Okay, so that's a type of potential energy. Okay, and so there's all these different types that you can convert between, but in a chemical reaction, whatever you have on the reactant side, as far as like energy of all of those bonds, the potential energy there, it has to then equal the product side. Okay, so you can't just create energy out of nothing. Okay. All right, and so this is just an illustration of hydroelectric power plant, what happens. And so this is a good illustration of the difference in energy. And so you've got some dam that is restricting the water here. And so you've got, if you think about it as an analogy of the height difference, so here to here, that is the difference in potential energy. Okay. And then as you are flowing the water in, it just is, turning this turbine that's connected to electrical generator. And so, that's just how simple these operate. So you're not, burning any fuel for these. It's just turning a turbine, and then the water goes out some outlet. And so in this case, you're converting potential energy to kinetic energy as it turns the turbine. Okay. All right, so thermal energy is another type of energy that is it's a kinetic type of energy because it's really the molecules themselves, atoms, molecules are moving around and bouncing off one another. Okay, so again, really energy is just two forms, large umbrella terms. And then you've got all these other ones like thermal, electrical, nuclear. All of those are subclasses of those, kinetic or potential. And then heat, just as a definition, is the amount of this thermal energy that is transferred from one object to another. And it's, I think as you realize, heat is always transferred from the hot object to cold. Okay. So if you have, a hot cup of tea sitting on your desk, in a short amount of time, it's going to cool off and it's going to kind of equilibrate to the temperature of your room. Okay. So it's going from hot to cold. All right. So another way you can illustrate the first law of thermodynamics that energy can neither be created nor destroyed is that the total internal energy of a system is constant. Okay, and so if this is your system, let's say just a Erlenmeyer flask with some reactants in here, let's say, then anything outside of that is your surroundings. Okay, and so in this chapter, we are going to talk about the two cases where heat, this is really as energy, but in this chapter, we're really going to talk mainly about heat. Okay, so heat can either flow into the system from its surroundings, okay, or if we have this isolated system, it can flow out. Okay, and and the definitions here is if we have heat that's flowing in to the system in this first case, this is called an endothermic process or reaction, okay? Whereas this one is exothermic. Okay, so where heat is being evolved, okay, so think of like burning a fossil fuel, something like that. Okay, so fossil fuel combustion, okay, is where you would have heat going out of your system. Heat flowing in would be, this one is harder to visualize, but this would be, for instance, a cold pack. Okay, so it's something where, and this is what's kind of counterintuitive, that heat is flowing into your system, so you would think that you would feel it getting hotter, right? It would be warmer. But it's actually, if you think about it as this, that you are sensing whether a system is hot or cold by touching it, right? And so if you are putting your hand up to this, is that even the right number of fingers? I don't know. Okay, so if you are touching this system, if you perceive it as cold, that means that heat is moving from your hand to the system. Okay, and so you sense that as, oh, that's a cold flask or something. And so these cold packs are, what I mean by that is, you can get these in the pharmacy or Walmart or something, and you crack it, and then it gets cold, right? And you can put it on your knee or whatever. And so one side has water, the other side has a salt, okay? And, it could be like an ammonium chloride or something like that. And when you when you crack it, now water is able to flow in and dissolve this salt, okay? And there's some salts that when they dissolve in water, they are endothermic, which means, they get cold, whereas others are exothermic, okay? And so we'll talk about that kind of tomorrow, the two varieties of those. But in that case, yeah, that would be endothermic. And then exothermic, this one's easier to visualize because if you are holding your hand against this in exothermic, now if it's releasing heat, you are going to feel that, right? Like, ow, right? So this is now, you perceive it as hot, okay? Because heat's being evolved from your system. Okay. So what we're going to look at in this chapter is really, this is talking about some delta E, and whenever you see delta, that's always going to be some final state minus an initial state. Okay, and so in this chapter, we're not going to deal so much with E, to be honest, but it's going to be enthalpy, is really a fancy word for heat. Okay, and that is delta H. Okay, so delta H is going to be the heat, if you will, of some final state minus initial. Okay, so that's really what we're going to look at in this chapter. Okay, so this is an example where, again, we're measuring heat here, so you can replace the E's with H's. But you're just measuring how much heat is in your product side. So that's your final state, right? So final minus your initial, okay? And you end up with, it's releasing 802 kilojoules of energy, okay? And so, if you do all of this, you will see a negative sign here, okay, which indicates, so if delta H is negative, then that means that it is exothermic. Okay, if delta H is positive, then that's endothermic. Okay, and one way to visualize that is if you look at a reaction as it occurs, so the reaction progress versus your enthalpy here. Whoops, I guess it's not really delta, just enthalpy. Okay, and in one case, you can have, some energy level of your reactants, and then it's going to go up, and then it could go down like that. Okay, so this, we can say this is the energy level of your products, and this is the energy level of your reactants. And this is something, this hump is something we're going to talk more about in Chem 132. This is called your like a transition state. Okay, and so just think of it that when you put reactants together, you generally have to supply some heat or a spark or something for them, so for instance, burning methane, you have to, ignite it, right? And so that corresponds to this increase in energy here. Okay, so that's called your activation energy. Okay, so how much energy does it take? If you're going to roll a boulder from here to here, you have to supply it with energy really just to get right here. And then it's going to automatically, through force of gravity, take over from that point. Okay, so that's called your activation energy. But anyway, in this chapter, we're really concerned not so much about that, but really what's the difference in energy here? Okay, from final state to where you started. Okay, so that's your delta H there. Okay, and so if it's a negative value, that means that the products have a lower energy level than the reactants did, right? Okay, so if you, if you have, I don't know, if this is 0 and that's minus 10, as just putting some values here, then delta H is going to be minus 10 minus 0. Okay, so it's going to be a negative value. Okay, the other side, so this is for exothermic. Okay, the other situation for endothermic would look like this. Where you start with some reactant, and then you're going to go again over that activation energy, and then you end up here. Okay, so now if you're looking at this difference here, delta H, now it's going to be greater than 0, right, or a positive value. So this is for endothermic. Okay, so again, if you're putting values here, let's say this is 0, and then this one we'll say is plus 10. Okay, now delta H is going to be 10 minus 0 is plus 10. Okay, so positive value. Okay, so that's just kind of illustrating for exothermic, the energy of the products is less, or look at it this way, that it's more stable. So products are more stable than reactants because they're lower in energy. Versus endothermic, the reactants now are more stable than the products. Okay? All right, so a negative sign, as soon as you see this, okay, so the delta E or delta H for this reaction is minus 802 kilojoules per mole of methane, let's say. That means it's exothermic, okay? It's releasing 802 kilojoules of heat, okay? All right, so the phase of these reactions is very, very important, okay? And so here is, a similar reaction. So this is just burning propane, okay? But in this case, it's the reaction where you're forming steam, okay? And that will release a lot of energy. So like over 2,000 kilojoules. And joule is just the, by the way, whoops, if I could spell. Joule is the standard or the SI unit of energy. So that's the J here, okay? You can think about it as how much energy, so it's the energy equivalent of lifting an apple to a height of 1 meter, something like that. There's a whole bunch of these analogies you can find on the web, but 1 joule is just picking up an apple and bringing it up a meter from where you started, okay, against the force of gravity, okay. And so, it doesn't take much energy, but this is, like 2,000 times that amount of energy required is released when you burn propane, okay. And so the difference here is if you form steam, it releases this much. If you form liquid water, now it's releasing even more heat, okay. So you have to pay attention, to what these phases are for all of your products and reactants, okay. And we'll see this when we actually do these calculations probably tomorrow, okay. Okay, so if you see a, so here there's no little symbol, it's just delta H. If you see a little degree symbol, all that means is that it was carried out under standard conditions, okay? And that usually means room temperature, so 25 degrees Celsius. All concentrations are 1 mole per liter, so 1 capital M here. And then 1 atmosphere pressure, too. Okay, so these three. So STP is standard temperature pressure, is 25 degrees, 1 atmosphere pressure, and then concentrations 1 molar. Okay. All right, so some other definitions. So enthalpy of fusion, vaporization, and sublimation. So if we look at this scenario of just water, okay, so if we go ice, and then we melt it, and then we boil it, okay, this is where the enthalpy of sublimation, or what am I doing? Fusion occurs, okay? So fusion means going really between solid and liquid forms, but all of these processes, these phase changes, are reversible, okay? And so in this direction, It requires heat, so it's going to be endothermic. Okay, they require heat. Okay, so for instance, for you to boil water, you have to plug in the kettle, right, or give it some heat. Okay, so if going left to right, it's all requiring. Going right to left is releasing heat. So those are exothermic processes, okay? And so that's why, for instance, when it first starts to snow, the uh, ambient temperature actually warms up a little bit because you're going here to here, okay, liquid to solid, and it's releasing a little bit of heat. That's an exothermic process, okay? And so delta H is going to be um, like a positive delta H in this direction, and it'll be a negative, that same magnitude, but negative in the opposite direction, okay? And minus delta H. Okay, so that's delta H fusion. This is vaporization between liquid gas. And then the one between solid and gas is sublimation. So that's your delta H of sublimation. Okay, so that's, one thing to think about, or one example to look at would be this. Okay, dry ice. Okay, so it doesn't melt, right? That's the beauty of it, if you will. You can put it in your cooler, use it, and at the end of the day, you don't have to dump out heavy water, okay? And so yeah, it just evaporates, okay? So this would be delta H of sublimation, okay? And so this is, an illustration of those, okay? Sublimation going right from solid to vapor. Then you've got fusion if you're melting it, and vaporization if you're boiling, okay? Enthalpy changes here. So again, if you have a negative value, that means it's exothermic, okay? If you have something that's reversible, so not all reactions are reversible, but in this case, if this one is reversible, then in the opposite direction, so in this direction it's minus, in that direction, right to left, it's now positive, but it's the same value. Okay, so the magnitude doesn't change, just the sign, okay, if you're reversing these reactions. Okay. All right. I'm not going to spend a lot of time on this. I guess in lab, you looked at an example of calorimetry, so how you measure these energy changes. Okay. And so that's constant pressure. So that's just, you can use like a styrofoam cup and just determine how much heat is being, released, for instance, during a reaction. If you do it, if you go on to take advanced chemistry, we have a couple of these upstairs actually in Dow. It's called a bomb calorimeter. So you actually get to work with bombs if you major in chemistry. So there's an incentive for you. Calorimeter, okay. And so it's called a bomb because you have a very, very thick-walled reactor in here, and you can put in, hydrocarbon, like a fuel, gasoline, for instance, in here, and ignite it, and then it's surrounded by water, and the heat that is evolved here is then absorbed by the water, and then you can actually calculate how much heat, burning so much, you'd have to measure this out. Let's say you put in 50 grams of gasoline, and then you can figure out how much heat that released when you burn it, okay? And so this is a little more specialized, but you're really measuring this heat that's either flowing in or out from your, material. And so where we're going to stop today is really with this one equation. And so heat capacity is really, so this is one equation that I will provide for you on the exam. So I'm going to give all the equations for you. Um, the ACS would have given them to you as well. So it's not that I'm being very very nice, but I think I am. And so uh, I'll give this equation to you. And what this is that's just the heat uh, that is either absorbed or released by some reaction. This is some constant. Okay, so that's really what's called the specific heat. So that will have to be given, or you'll solve for it. Okay, this is the mass of your material, and then that's your change in temperature. Okay, so final temperature minus initial. Okay, and so I just want to kind of put that equation out there. Where we're going to start tomorrow then is we'll look at equation or questions where you're actually going to apply this formula. Okay, and then we'll finish off the rest of the chapter. All right, so any questions before I sign off? Okay. All right. Well, have a good rest of the day, everybody, and see you tomorrow.